So earlier this week, I looked at the use of serializable transactions in MySQL and Lucee CFML to enforce unique naming constraints within the application layer, meaning I wasn't using a unique index in the database to enforce the unique naming. I was moving that logic up a layer into the application. And I was using this widgets table, and in that demo, I claimed that the locking within this serializable transaction was based on the user ID. So today, I wanted to follow up with a quick exploration to demonstrate that the locking is indeed scoped to the user ID and not accidentally doing a full table scan, which would also have enforced unique naming, but at a much higher cost to performance. Now, this widget table has the user ID, and each row is supposed to be owned by a user ID, and then there's the name of the widget. That's really the primary focus here. But if we look at the index, what you can see is that I have an index by user, which is indexed on the user ID. And it's this index structure which allows us to create a lock based on the user ID instead of the full table scan. So to explore this, let's jump into the Cold Fusion code. What we're going to do is try to affect rows within the widget table that are owned by two separate users. And what we want to see is, does the serializable transaction for the first user impact the execution time for the serializable transaction on the second user? If the row locking was not user ID specific, then these two timings would collide. If they are user specific, then these should operate independently. So we have our Sarah ID and our John ID, and we have two widgets out of the gate that we're creating here. And then what we're going to do is spawn three different asynchronous CF threads, two that affect Sarah and one that affects John. And we're going to look at the execution times of both of those. So in the first Sarah thread, what we're going to do is insert a completely new widget. And her widget needs to be uniquely named. And you can see that we have a serializable transaction here, just as we did with the demo from earlier this week. And in between the current name check and the creation of the widget, we're sleeping for 3 seconds. So essentially this 3-second sleep here is going to hold this serializable transaction open, and it's also going to convert the underlying select here into a select for update or a select for shared lock. I can't remember what the exact terminology is, which means that all of the rows scanned in this select are going to be locked for the duration of this transaction. So we then have a second Sarah thread, and all this one is going to do is try to update the name of that first widget that we created. So again, our two Sarah threads are creating a totally new and second widget for Sarah, and then going back and renaming the first widget. And this one has a sleep of a second, and that's basically to make sure that we get to this point before that second thread can start to execute, which means that this rename operation takes place in the middle of this serialized transaction from the first thread. So those are our Sarah threads. Then we have a third thread for John, and John is basically going to do the exact same thing that the first Sarah thread is doing, which is that it's going to have a serializable transaction. It's going to try to insert a new widget, check the unique naming, and then insert the widget should the name not yet exist. And this time we're going to use a sleep of a single second. And again, that's just to make sure that we get to this part of the transaction for Sarah, but not have it sleep as long, to make sure that the execution times are different. And then what we're going to do is just wait for all of those threads to rejoin the parent request, dump them out, and then look at our data tables. So let's jump over into the browser and let's refresh, and it'll hang here for a few seconds while the transactions are running. And if we look at the two Sarah threads, Sarah insert thread and Sarah update thread, you can see that they both ran for about 3 seconds. And again, if we jump back into the code, we expected the first thread to run for 3 seconds because it actually has a sleep for 3 seconds. But the second thread only has a sleep for 1 second. And again, we're seeing that update thread sleep for 3 seconds. And that is because, again, this sleep of a second here puts it inside of the overlapping serializable transaction. And what we're seeing is that this rename widget is essentially being now blocked by the row locking being applied by this transaction. So we can see that at least all of the Sarah records have been blocked and serialized. in terms of their execution order. But if we look at the execution time for John's insert thread, it only executes for about a second. And again, if we jump back into the code, we can see that John's insert thread only slept for a second. And what we can tell here is that because this executed quickly, relatively speaking, it was not being blocked by the serializable transaction for Sarah, which demonstrates that the row level locking for that serializable transaction is user ID specific, meaning that this update, which affected a different user ID, was not affected by the locking applied to this particular user ID. And at the top of this video, I said that that is because of the underlying index. So actually, if we jump back into our code here, into our database, and we look at the index, if we actually just remove this index, so essentially there is no index structure now that limits by user ID, which means that when we go to run this isWidget with name exists for Sarah, the database can't limit this call to a particular set of rows. Instead, it's going to have to do a full table scan, which means that it's going to have to apply that gap locking and that next key locking to the entire table. And now if we rerun this Cold Fusion code, we should get a database transaction deadlock. And there you can see we do get the deadlock. And again, that is because there was no index that allowed this select to be limited to a particular subset of rows. It was a full table scan, which means that the lock was applied to the full table, which means that this serializable transaction for Sarah does impact this serializable transaction for John. But again, if we come back in here and let's add an index. And we can do user ID, and let's just save that. So now that we have a index that applies to a particular subset of rows based on user, again, if we rerun this, we should see the outcome from our first test, which is that both the Sarah threads run for about 3 seconds and the John thread runs for about a second, because the underlying index structure allows the row level locking to be limited to a particular user ID, allowing Sarah's ID and John's ID to operate independently. So I feel like I'm finally getting a better understanding of how the row level locking within a transaction works, or I guess I should say specifically when a serializable transaction works. And this will allow me a little bit more flexibility in how I apply transactions within my Cold Fusion and MySQL applications going forward.